Hello, Fig here again, and we're going to look at another force problem and an application of Newton's second law. But this time our forces are not simply just in the horizontal or just in the vertical direction. So we'll have to be a little bit more careful with this problem, but let's take a look. Now, again, as with any problem in physics, having a good sketch in front of you to work with is very important. Now, the question this time involves an object, a mass, suspended by ropes. So here, an object is suspended by cords as shown in the diagram below. So here are a ceiling and a wall, and I have three cords with a mass suspended on the bottom cord. The diagonal cord has a tension Fa equal to 180 newtons. And the horizontal cord has tension Fb. Find the tension Fb and the mass of the object. So, at first it might be confusing about where to begin in this problem. This is why taking a step back and making sure you understand the physics that's going on in the picture before you dive in and start trying to do math. So the first thing we want to note is that the entire system is motionless. This is an example of what's called a statics problem. So I'm going to make a note that my acceleration in this problem is 0. Now, I'll still use Newton's second law, which says that F net equals ma, the mass times the acceleration, but it means that these forces must all cancel out and add to 0. So, but remember, this is a vector equation. So, on the picture, if we put it on the vectors, now the forces are as follows. The description says that this force right here along this string is force vector Fa. Now, I know it, the value of it, but I'm not going to put that value on the picture. I don't want to put too much confusing numbers on. I'll just put Fa, and I'll put a little check that I actually know what that is. Now notice that the diagram also tells me that the angle of this rope is 53 degrees. The problem then goes on to say that the horizontal cord, that's this cord here, has force Fb. Now, there's a third cord in the picture, this cord here. And obviously, you might be able to see right away that this cord has to be supporting the weight of the hanging mass. But really what's going on, if I isolate the free bodies, there are actually two force problems in this picture. There is a tension here going down at this point where the three ropes come together. I'm going to call that Ft. But then the mass here has a weight vector pointing down, Fw, which is equal to mass times the gravitational acceleration. Now, remember that g is the acceleration that objects fall on Earth. That is, g is a constant. Gravitational acceleration g equals 9.81 meters per second squared. Now, that acceleration appears in the problem even though nothing is actually moving, because that is how we actually calculate weight. So I can see that if I can solve this force, find this weight, I can find the mass of the object. Now, how does this tension relate? Well, you may recall that on any one cord or string there can only be one tension. So the tension pulling down on this point must be the same as the tension pulling up on the mass. So I actually have two force pictures here. I have one, the point where the string is tied, and that force diagram I'll make right here. At that point where the three strings are tied, I have the following forces. I have Fb, I have Fa going up at this angle, and I have tension Ft. Now, drawing your forces like this is just a little bit easier to see what's going on without all the rest of the picture confusing it. Now, let me do the mass. I'll do that right below. On the mass, I have the forces Fw, the weight, and I have Ft, the tension. Now, I have a similar problem that we did when we were looking at the boxes being pulled horizontally. I need to decide what I'm calling the positive direction and what I'm calling the negative directions. But now I also need to worry about the vertical as well as horizontal. So again, on my picture, I'm going to make a little diagram. Now, I'm going to call to the right the positive x direction, and I'm going to call to the left the negative x direction, and I'm going to call up a positive y direction, and I'm going to call down the negative y direction. Now, this is basically just using the coordinate system used in Cartesian coordinates in mathematics to give me a reference. The physics is are the forces pulling on the strings and supporting the weight. What we call positive negatives, well, this is just a math convention. I mean, actually, if I wanted to draw these forces to scale, I could actually add them tip to tail graphically. I don't know if you remember graphic vector addition, but that would be cumbersome. So what I would like to use is to be able to use a little trigonometry to actually solve this problem. Well, we have to be a little bit careful here. Well, you might see right away that the place to start will be the tension and the weight. Because that box is not moving, I'll now put in my signs. This weight is now a negative mg. Sorry, get the right color here. This tension here will be negative. Tension going up in the box would be a positive Ft. This Fb I need to make sure is negative in my equations. But now what to do with Fa? Well, Fa is both pointing in the positive y direction, but also in the negative x direction. So the way we handle a vector pointing in two directions like this is to separate it into two new vectors. Now, these aren't on the picture because they don't really exist, but if I have a vector pulling up at an angle like this, it's going to be equivalent to a vector pulling across, and I'll put it in green. Now, it's not always the best strategy to put these components, and these are called vector components, on the picture. But I could represent vector A as some vector in the x direction, I'll call it VFAX, and some vector in the y direction. Because these two vectors combined act like vector A. Now this picture is already getting complicated, so I'm going to put this aside and let's work with new diagrams on the second sheet of paper. We'll start with the mass, because we can see that if nothing is moving here, the tension and the weight have to be the same size and in opposite directions. So let's start by looking at the mass a little bit more clearly. The hanging mass has two forces acting on it. The weight, which I will now represent by mg, and a tension vector, Ft. Again, I use Newton's second law that F net equals mass times acceleration. But this is 0. So I don't have to worry about, it's not an O, there we go, it's a 0. I don't have to, so there's no acceleration given to me, and I don't know what the mass is, but I know that this side of the equation must be 0. So let me put in the forces, and I'll put in the signs now. This means that the tension minus mg, and I've put in the negative sign, so again I've dropped my vector hats, equals 0, and I see that tension equals mg. Now, there's the mass I want, and you might object that, but we don't know the mass. Actually, we're looking for the mass of the object, so what good does this do me? Because I don't know the mass and I don't know the tension. Well, leave that aside for now. This is why it's important not to focus on numbers. I know that once I find out what Ft is, I can now find the mass from this equation. So the next step is, let's look at these forces that come together where the string is tied. Now those forces, I'll do right here. So acting there, again, have the force Fb. I have a force going up at an angle, Fa, and I want to remind myself that I actually know this angle. Theta equals 53 degrees, and I have Ft. Alright, now, so what do I do next? Well, I know how large Fa is. It's 180 going in that direction. So what I need to do is break Fa into components. Now I'm going to do that over here, and then we'll look at a new force picture with the components of Fa. So if I take a look at vector Fa, I want to break this into two new vectors, Fax and Fay. Now these vectors complete this triangle. That is, if I imagine that I pick this vector and redraw it over here, you can see that when I add vector Fax and vector Fay, I actually do get the vector Fa. Now, they told me that this angle with the horizontal was 53 degrees. Well, if that angle is 53 degrees, then because these are all the Fay here, I've just drew twice, they make parallel lines, that means that this angle here must also be 53 degrees. Now, I have a right triangle. So I can use trig, where I have the adjacent side of the triangle, I have the opposite side to the angle, from the angle of the triangle, and this is the hypotenuse. Alright, and again, my picture right now is a little small and getting a little complicated, so what I'm going to do is, yet again, just redraw it so it's easier to see, and I'll make it nice and large. So the original vector Fa is the hypotenuse of the triangle. Fax is this side of the triangle. Fay, that is that side of the triangle, with the angle here being 53 degrees. Now, I'll leave Fay is really over here at where the original vector starts, but I'll just leave this here to make it easier to see the triangle. Well, what I need to do now is set up my trig functions. I know that the sine of the angle is equal to the opposite side of the triangle divided by the hypotenuse. Well, in this case, that's going to be then the sine of the angle is equal to the opposite side of the triangle is the component I want, Fay, divided by the entire length of the vector Fa. Now, note, before we go further, we know what the angle is in the problem, and we know what the actual vector Fa is. So I can now find this component by rearranging and saying that Fay is equal to the original vector Fa times sine of that angle. Now I am not putting in the number right now because I don't want to get confused with it with calculations. I'll make the same note that cosine of the angle, which is the adjacent side of the triangle over the hypotenuse, is going to be equal to FAX, the horizontal component, divided by FA. And similarly, FAX is equal to FA cosine of the angle, where again, I know the angle and I know FA. So FAY and FAX I can calculate. Alright, so you might be asking yourself, why? Why do I take one vector and I split it up into two? Doesn't that make the problem more complicated? Well, leaving the calculations part of it alone, let's see why we want to do this. Now remember what the actual problem is. I have three vectors, FA, FB, and FT acting at that point. But what I would like to do is split it up into two separate problems. I would like to look at just the forces acting in the x direction, and just the x direction, and just the forces acting in the vertical, the y direction. Well, by doing the components, FA is now replaced by two simpler vectors to work with. I again have vector FB, and I have tension FT. Now remember, this vector FT is actually equal to mg, so once I find this, I'm okay. Now, instead of putting FA back on the picture, I'm going to just draw in the components. FA is being replaced by two new vectors, FAY and FAX. Now this is actually now a much simpler problem. I don't have to worry about angles anymore. Remember, I know the size of FAY and I know the size of FAX, and so I can now work in the problem in the x and the y direction. Well, let's work with the x direction first. So if I look at the forces in the x direction, I would say that the net force, the piece of the net force in the x direction, is equal to mass times acceleration, the piece of the acceleration in the x direction. Well, there is no acceleration in this problem. The acceleration is 0. That means it's not going back or forth in the x direction or up and down the y direction. So I replace this with 0. Well, my forces in the x direction are simply FAX and FB. So I have, you see the problem I did originally? Back here I made a mistake. This is actually not a negative sign. This is a positive sign. That probably confused you. My bad. I'm sorry. It is difficult to talk physics and draw physics at the same time. So, back over here, I get that FB in the positive direction minus FAX in the negative direction equals 0, or, well, this is the first part of my problem solved. FB must be equal to FAX. Well, I'm going to just replace FAX, this component, with what we calculated before using trigonometry, that FAX is going to be the original vector FA times cosine of the angle. So I get that FB equals FA times cosine of the angle, or FB equals 180 newtons times cosine 53 degrees. Now, when we calculate this, we can use a calculator, and you want to be careful to make sure your calculator is actually in degree mode. Now, I have my calculator here, and so I'm typing in the cosine of 53, and I get that this is actually going to be 180 newtons times the decimal 0.6018. There's more digits afterwards, but that's 4 significant figures is fine. And I find that that force FB, the size of it must be equal to 108 newtons. And that's the first answer. Well, now let's work with the y forces. In the y direction, again, I have the net force in the y direction is equal to the mass times acceleration in the y direction. But again, that is 0 because nothing is moving in this problem. There is no acceleration. So I'll then just add my forces. I have Fay, which is a positive force, now minus Ft equal to 0. And I will now make the substitution that I know this tension is actually mass times gravity. So I get Fay minus mg equals 0, or mg will be equal to Fay. But this was equal to Fa sine 53 degrees. So we have that the mass times gravity for the hanging mass is equal to 180 newtons times, and again, I'll go to the calculator to check for the sine of 53 degrees. And this will be the decimal 0.7986. Again, there's more digits, but that's plenty for this for the three significant figures. So when I multiply that out, I get that this is 143 newtons. Actually 143.7, which is approximately 144 newtons. Now that's not the mass of the object, that's the weight of the object. To find the mass of the object will be equal to 144 newtons divided by gravitational acceleration g, which is 9.81 meters per second squared. So when I do that out, 14.7 kilograms. And there are my two answers for the problems. Now clearly you have to be much more careful when you have vectors pointing in both the x and the y direction and with an angle such that you have to find components. Now, is there a way, you can see that there's several places that you could make a calculated mistake. Is there a way to check that we can be confident in our answer? And you can if we go back to where we broke the vector Fa into components. Now, we found that Fay from our calculations was, well, we found that Fay, which was equal to 144 newtons, and we found that Fax was equal to 108 newtons. Now, I can use the Pythagorean theorem to double check to make sure I took my components correctly. Pythagoras said that if I call the hypotenuse of the triangle C and the two legs A and B, I know that C squared is equal to A squared plus B squared, or that C equals the square root of A squared plus B squared. So I know the size of the triangle, they're my components, so I can actually check this out. I can say that C is equal to the square root. Well, that'll be A is my y component in this case, that's 144 squared. B is 108 squared. When I do this out, 144 squared plus 108 squared, and then I take the square root of that number, I get 180, which is in fact the length of Fa. So that's just a nice way to double check that you took your x and y components correctly, because by Pythagoras they should, the Pythagorean theorem should yield the length of the original vector, and it does. So just a quick summary, it's worth going back because a lot happened in this problem. We start by noticing that the tension pulling down the rope had to be equal to the weight of the block. Strictly if you're comfortable with that, it's not necessary to make a separate force diagram, but it's useful just pointing that out separately. Now, once I know that, then I had the three forces acting on the point where the string is tied. Whenever I see a vector at an angle, I will be splitting those vectors into x and y components. And although it's confusing if you do it all in one picture, if you're careful about your components, your force problem will become a much simpler problem where you only have to deal with vertical forces in the y direction, horizontal forces in the x direction, and as long as you're careful organizing your information, you should be finding a problem. So this also brings home why it's so important to write everything out in physics. If you try to do this on a calculator without writing the steps down, there are so many places that you can make simple mistakes, and there will be no way to go back and check your work. So always try to organize your work, what's going on in the x direction, what's going on in the y direction, and double check your components add up to the original vector is always a good idea as well. Okay, I hope this helped solving problems in 2 dimensions, and I hope you see the importance of making force diagrams, and good luck with the rest of the assignment.